Welcome. Tonight, our journey takes us to a version of our own planet that defies our modern understanding of geography, a world that is, in its own way, as alien as any distant jungle moon. We are traveling back to a time of profound, almost universal warmth. A time when the very concepts of ice cap or polar desert did not exist. A time when the entire globe, from the equator to the very poles, was cloaked in a single, vast and humid blanket of green. We are journeying back to the time when Earth was a rainforest planet. Imagine our world, but without its vast, white, silent continent at the bottom. Picture Antarctica not as a desolate, miles-thick sheet of ice, but as a land of lush, temperate forests, its dark shores lapped by a cool, open ocean. Imagine traveling to the opposite end of the world, to the high Arctic within the polar circle, and instead of finding a frozen sea of ice floes, you find warm, swampy, subtropical forests, a place where alligators and turtles sun themselves on the banks of lazy rivers, a place where palm trees and broad-leafed plants grew, enduring not a winter of cold but a long, strange, 3-month winter of warm, humid and total darkness. This world is not a fantasy. It is not a speculation. It is a memory written in the stone of our planet, a period known as the Eocene, the long warm dawn of the age of mammals. It was a hothouse world, a time when the planet's atmosphere was saturated with greenhouse gases, trapping heat and creating a global climate of almost unbelievable mildness. Tonight, we will explore this lost green world. We will meet the strange, giant creatures that inherited the planet after the dinosaurs vanished. We will walk through the silent, dark polar jungles. We will float on the warm, sluggish Arctic Ocean, and we will witness the slow geological clockwork that, after millions of years, finally broke this fever, plunging the world into the long, cold cycle of ice ages that would eventually set the stage for our own. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It is always a deep comfort to know who is joining us on this voyage to a lost, warmer Earth. Now, dim the lights. Perhaps turn on a fan for that soft background hum. Imagine it as the sound of a warm, humid wind moving through the leaves of a forest that has not existed for 50 million years. Let the familiar, icy image of our poles dissolve, and let's ease into tonight's journey together. To understand how this new, hothouse world of mammals could be born, we must first travel to the moment just before its dawn, to the profound, echoing silence that followed the end of the age before it. We must begin in the quiet, wounded world that the dinosaurs left behind. The Cretaceous period, the long, final and magnificent act of the age of dinosaurs, had ended in fire and darkness. The Chicxulub asteroid, that 10-kilometer wide rock from space, struck the Earth with a force that is almost impossible to comprehend, a violence that tore the very fabric of the biosphere. The world was plunged into the catastrophic, sunless cold of the impact winter, a global shroud of dust and soot that lasted for months, perhaps years. And when the dust finally, slowly, settled, and the weak, pale sunlight returned to the surface of the planet, it illuminated a world that was, in a profound and chilling sense, empty. This was the dawn of the Paleocene epoch, the first chapter of our modern Cenozoic era. But it was an age born in silence. The great thundering footsteps, the deep resonant calls of the hadrosaur herds, the terrifying roars of the tyrannosaurs, the leathery wing beats of the giant pterosaurs, all of it was gone. The dynasty that had ruled the planet for 165 million years had been, in a geological instant, erased. Imagine standing in a forest in what is now North America, just a few thousand years after the impact. The silence is the first thing you would notice, an immense, heavy, and unnatural quiet. The world has been scrubbed clean of giants. The forests themselves are skeletal, spectral. The initial firestorms would have consumed vast swathes, and the long, dark winter that followed would have killed countless more. The world is a pale, brown landscape of shattered, burnt trunks, rotting logs, and perhaps a low, opportunistic carpet of resilient ferns, a disaster flora, spreading quickly to take advantage of the empty, sunlit ground. The oceans, too, were devastated. The great predatory mosasaurs and plesiosaurs were gone. The ammonites, with their beautiful coiled shells, had vanished forever. The very plankton at the base of the food web had collapsed, and the seas were quiet, acidic, and struggling to recover. This was the Great Silence. The world's complex, vibrant ecosystems built up over millions of years had been shattered. The slate, in a very real sense, had been wiped clean. But it was not a dead world. Life, in its most humble, most resilient forms, had endured. It had hidden, it had waited. And now, in this new, empty, silent world, these survivors began to emerge, blinking from the darkness. The survivors of the great cataclysm were not the strong, not the large, and not the dominant. The very traits that had defined success in the Cretaceous world, immense size, high metabolism, specialized diets, had become, in the face of the impact winter, a fatal liability. The giants were the first to fall. The creatures that inherited this new broken earth, this Paleocene dawn, were the humble, the small, the adaptable, the ones who could hide. Imagine the world in those first difficult centuries after the dust settled. The forests are ghostly, the food webs shattered, and scurrying, almost unseen, through the leaf litter in the shadows of the rotting logs are the mammals, our own ancestors. For the past 100 million years, they had lived in the shadow of the dinosaurs, a quiet, nocturnal, and largely overlooked lineage. They were, for the most part, small, perhaps no larger than a modern shrew, a rat, or a badger. They lived in burrows, in hollow trees, in the cracks of the world, their lives spent avoiding the crushing footsteps of the giants. And this very lifestyle, this specialization in being small, secretive, and adaptable, became their salvation. When the asteroid struck, they were perhaps already hidden. A creature living in a deep, insulated burrow would have been shielded from the worst of the initial, searing heat pulse that ignited the world's forests. They would have been insulated from the deepest, most immediate chill of the impact winter that followed. And crucially, their diet was not the fresh green leaves of the canopy. They were generalists. They were insectivores, their sharp, precise teeth perfect for eating the grubs, worms, and insects that likely survived in the soil and the rotting wood. They were omnivores, capable of eating anything, roots, tubers, perhaps the fungi that flourished on the global carpet of decay, and, grimly, the very carcasses of the dying giants. They were creatures built to survive on the scraps of a broken world. They were joined by the other great survivors, the birds. Not all birds, of course. The bizarre, toothed marine birds like Hesperornis vanished with the great marine reptiles. But the ancestors of modern birds, perhaps small, ground-dwelling, or seed-eating creatures, possessed the same advantages as the mammals. Their small size meant they needed less food. Their beaks, perhaps, were perfect for cracking open the one vast and dormant food source that could survive the darkness. Seeds. Seeds, the planet's own ark, lying dormant in the soil, waiting for the light to return, would have been a crucial larder for the small creatures that could find and eat them. And in the rivers and ponds, the story was the same. The great, active marine predators were gone, but the freshwater ecosystems, perhaps buffered from the worst of the atmospheric shock, proved to be a vital refuge. Crocodiles and alligators, creatures capable of entering states of long metabolic torpor, their hearts slowing to an almost imperceptible beat, could simply wait out the darkness and the cold, surviving for months, perhaps years, without a substantial meal. Turtles and tortoises, with their slow metabolisms and protective shells, endured. Amphibians, the frogs and salamanders, burrowed deep into the mud, their entire lives a cycle of dormancy and patience. These, then, were the inheritors. The small, the burrowing, the generalist, the seed-eating, and the slow of metabolism. They were not the kings and titans of the old world. They were the meek, the quiet, the resilient. They had made it through the fire, the darkness, and the cold. They now found themselves in a world that was, for the first time in 165 million years, entirely, completely empty of giants. The throne of the world was vacant, and these small, trembling, nocturnal survivors, blinking in the faint, returning sunlight, were about to embark on the slow, patient, and magnificent process of refilling that void. The quiet, green, and cautious dawn was beginning. The survivors had inherited a broken, silent, and empty world, but the Earth itself, in its profound geological patience, does not remain broken for long. The darkness of the impact winter had passed. The sun, that great distant engine of all life, was shining once more on a planet scrubbed clean of its former masters, and life, in its quiet, tenacious, and irrepressible way, began to reclaim the void. This was the Paleocene epoch, the first 10 million years of the new era. And it was not an age of sudden, vibrant explosions. It was an age of slow, cautious, and almost hesitant recovery. Imagine the land in the first few millennia. The disaster flora, the opportunistic, fast-growing ferns that had formed a low green carpet over the initial devastation, began to give way. From the soil, the seeds and spores of the more complex plants, the ones that had survived the long darkness, began to sprout. The flowering plants, the angiosperms, which had already begun their rise in the Cretaceous, now had their true opportunity. With the great, browsing, herbivorous dinosaurs gone, they were free. Slowly, the great forests returned. But they were, at first, strange, ghostly forests, perhaps low in diversity, dominated by just a few hardy, fast-growing survivor species, like relatives of modern sycamores or laurels. The great ancient conifer forests also began to recover. The planet was, slowly, turning green again. And as this new green foundation was laid, the surviving animals, those small nocturnal mammals and birds, began to respond. The world, for them, had fundamentally changed. The greatest, most terrifying ecological pressure of their entire 100 million year existence, the dinosaurs, was gone. The throne was empty. The niches were open. And for the first time, mammals dared to step out of the shadows into the daylight. This was their moment. This was the age of mammals at its very dawn, and it began with a burst of evolutionary experimentation. Creatures that had been for millions of years confined to the size of a rat or a badger, now, in the absence of giant predators, began to grow. And they grew fast, geologically speaking. Within just a few million years of the dinosaurs' disappearance, the world was suddenly filled with an array of strange, archaic, experimental mammals, the first rough drafts of the lineages that would come to dominate. Imagine the forests of the Paleocene, filled with these new creatures. They are not yet the familiar forms we know. We see the rise of the first primitive hoofed animals, the condylarths, not yet deer or horses, but strange generalized creatures experimenting with a herbivorous diet in a world free of giant sauropods. We see the rise of the first large carnivorous mammals, the creodonts, like Oxyaena, strange weasel-like or cat-like hunters, the first mammals to attempt to claim the apex predator niche left vacant by Tyrannosaurus. And the birds, those other great survivors, were also exploding in diversity. Having inherited the skies from the vanished pterosaurs, they radiated into countless new forms. And on the ground, some birds also took the vacant throne of the large predator. In the forests of the Paleocene, creatures like Gastornis, the terror bird of Europe, evolved, a 2-meter-tall, flightless giant with a massive, powerful beak stalking the new mammalian herbivores. This was the Paleocene recovery. It was a strange, transitional world, a world of survivors, a world of first drafts, a world of evolutionary experiments, all unfolding in the quiet, recovering, greenhouse warmth of a planet rebooting itself. Life was returning, finding new forms, new pathways. But this recovery, this new mammalian experiment, was not happening on the familiar map of the world we know today. It was unfolding on a planet whose geography was still a lingering echo of the age before, a world whose continents were still clustered in a way that would set the stage for the next profound and global transformation. This geography, the stage for the dawn of the age of mammals, was indeed a lingering echo of the Mesozoic. The world was still in the late stages of Pangaea's long, slow-motion breakup. The continents were not in their familiar modern positions, and the oceans that separated them were different in both shape and character. Imagine the North Atlantic Ocean. It was not the vast, wide, cold ocean of today. It was, in the Paleocene, a much narrower, younger, and perhaps warmer sea. Greenland, North America, and Europe were still clustered relatively close together, not yet fully separated into the distinct, distant continents we know. To the south, the South Atlantic was also still forming, as Africa and South America continued their slow tectonic divorce. Antarctica and Australia, which had clung together for eons, were just beginning their final separation, starting to open the seaway that would one day isolate the southern pole. India, a lonely island continent, was on its long, final, inexorable drift northwards, heading for its slow-motion, mountain-building collision with Asia. This different, more clustered arrangement of the continents meant that the great global ocean currents, the planet's circulatory system, flowed in different patterns. The world, still lacking significant ice at the poles, was dominated by a warmer, perhaps more sluggish, global circulation, distributing heat more evenly across the planet, from the tropics to the high latitudes. This was a world primed for warmth. It was a world without the great, cold-generating polar ice caps that act as our modern planet's refrigerators. It was a world whose geography naturally favored a warmer, more stable greenhouse state. The Paleocene recovery, this quiet, cautious refilling of the empty world, unfolded under this stable, warm greenhouse climate. For nearly 10 million years, life slowly, patiently rebuilt itself. The forests spread, the mammals grew, experimented. The world settled into a new, gentle, warm equilibrium. It was a good, quiet, stable time to be alive, a time of slow rebuilding. But this specific interconnected geography, this world of still clustering continents and unique warm water ocean currents, held a hidden, sleeping vulnerability. The planet's climate system, already running warm and stable, was balanced on a delicate geological knife edge. It was a world primed not just for warmth, but for extreme heat, and all it needed was a trigger, a single, sudden, and catastrophic geological event that would, in a geological instant, push the planet's thermostat past its breaking point, unleashing a torrent of greenhouse gases and plunging the world, not into cold, but into a profound, lasting, and planet-altering fever. The quiet dawn was about to end in a blaze of fire. That blaze of fire, the trigger that tipped the warm Paleocene world into a true hothouse, was not a sudden meteor nor a war of the gods. It was instead a profound geological spasm, an event buried in the rock record that marks one of the most rapid, extreme, and transformative natural global warming events in our planet's entire long history. We call it the Paleocene-Eocene thermal maximum, or the PETM. It occurred with shocking suddenness around 56 million years ago, marking the boundary between those two epochs. Imagine the Earth coasting in its stable, post-dinosaur greenhouse warmth, and then, in a geological instant, perhaps over a period of just a few thousand years, a mere heartbeat in the planet's life, something, somewhere, released a colossal, almost unimaginable amount of carbon into the atmosphere and oceans. Trillions of tons of it. A vast planetary-scale injection of greenhouse gases, primarily carbon dioxide and methane, dwarfing even the amounts released by the Deccan traps or the Siberian traps that had triggered the great extinctions. The effect on the planet's climate system was immediate, violent, and profound. The atmosphere, already warm, was suddenly wrapped in an impossibly thick, new, heat-trapping blanket. The thermostat, which had been set to warm, was suddenly, violently, cranked to high. Global temperatures soared. The rock record, in its patient chemical signatures, tells us of a rapid global fever, with average temperatures climbing by 5 to 8 degrees Celsius, that's 9 to 14 degrees Fahrenheit, above their already warm greenhouse baseline. This was not a gentle, comfortable warming. This was a spike. The tropics, already hot, may have become lethally so, perhaps reaching temperatures that were almost unlivable for large animals. But the most dramatic, most profound change occurred at the poles. The high latitudes, which had perhaps been cool and temperate, now became subtropical. The Arctic Ocean, that once distant cool sea, warmed to the astonishing, almost unbelievable temperature of a modern temperate swimming pool, perhaps reaching 23 degrees Celsius or 74 degrees Fahrenheit. This was the Great Fever, the true beginning of the rainforest planet. It was the event that shattered the last lingering vestiges of the old world's climate and ushered in a new, strange, and profoundly hot reality. The Earth, for the next several million years, would be a planet almost without an equator to pole temperature gradient. A world where the average temperature in the Arctic was perhaps only 10 or 15 degrees different from the average temperature at the equator, rather than the 40-degree difference we see today. It was a world of almost uniform, global, humid warmth. But this sudden, violent atmospheric event was not just a heat wave. It was a dual crisis. As the oceans, that great planetary buffer, tried to absorb this immense sudden flood of carbon dioxide, another catastrophe was unfolding beneath the waves. The water itself was turning toxic, setting the stage for a silent, unseen, and deep global crisis in the sea. This was a dual crisis. As the oceans reeled from this sudden injection of carbon, the entire planet was gripped by this profound fever. But what could do this? What natural force could, in a geological instant, release trillions of tons of carbon into the sky, triggering an event of such terrifying, world-altering power? The answer, scientists now believe, lies not in a slow, steady process, but in a sudden, catastrophic geological event tied to the very plumbing of the Earth itself. The prime suspect in this vast planetary detective story, the smoking gun for the Paleocene-Eocene thermal maximum, is not an asteroid from space, but a vast explosion of gas from within the Earth, specifically methane. We must understand that the Earth's oceans and the deep, cold sediments of the continental shelves contain vast, unimaginable quantities of this potent greenhouse gas. It is not always a free gas. Under the immense pressure and the cold, stable temperatures of the deep sea floor, methane gas and water can combine to form a strange, ice-like, solid substance, methane clathrate, or fire ice. Imagine vast, deep subterranean fields of this stuff, a solid, frozen deposit of concentrated, pressurized methane, held in a fragile, icy cage, stable only as long as the pressure is high and the temperature is cold. It is a sleeping dragon, a colossal reservoir of carbon locked away safely in the planet's deep, cold mud. Now, let us return to the world of the Paleocene, 56 million years ago. The planet is already warm, but in the North Atlantic, something new is happening. The continents of North America, Greenland, and Europe are in the final violent stages of tearing apart. The North Atlantic Ocean is being born, and this birth is not gentle, it is volcanic. A massive surge of volcanism, known as the North Atlantic Igneous Province, begins to rip the crust apart. Immense fissures open, pouring out flood basalts, a process that would build the foundations of Iceland, Greenland, and the undersea ridges that now separate the continents. And this rising, superheated magma, this tide of molten rock, did not just pour into the cold sea, it pushed upwards into the thick, organic, rich sediments that had been accumulating for millions of years on the seafloor. This is the trigger. Imagine this, the rising 1,000-degree magma, like a vast, hot electric plate, pushing up from below into the deep, cold, stable layers of methane clathrate. The fire ice is suddenly, catastrophically heated. The icy molecular cage that held the methane captive for eons instantly fails. It melts, it vaporizes. The result is a methane burp, a catastrophic runaway geological release of perhaps thousands of gigatons of pure methane gas erupting from the seafloor. It would not be a gentle fizz. It would be an explosive, churning, massive column of gas bursting from the deep ocean, surfacing and releasing itself directly into the atmosphere in a geological instant. And methane is a greenhouse gas of terrifying power, far more potent in the short term than carbon dioxide, trapping heat with vicious efficiency. This methane burp hypothesis, perhaps compounded by the magma also cooking ancient buried oil and coal deposits, provides the engine for the PETM. It is the sudden, massive, and almost unimaginable injection of carbon that the climate models require. It is the event that lit the fuse. The sky, in effect, caught fire. This sudden, immense blanket of methane and its oxidized byproduct carbon dioxide was the cause of the profound global fever. The planet, already warm, was suddenly, violently, pushed into a new hyperthermal state, a true hothouse, a world from which it would take over 100,000 years to recover. This intense runaway warming, this new global fever, was the true birth pang of the rainforest planet. It was the event that would melt any lingering polar ice, that would turn the oceans into warm baths, and that would set the stage for the bizarre, jungle-like world that would flourish, impossibly, at the very poles of the Earth. The oceans, for all their vastness, are not inert. They are a complex, living, chemical soup, a dynamic buffer that absorbs vast quantities of gas from the atmosphere, attempting to maintain a delicate planetary equilibrium. But the sheer staggering speed and volume of the carbon release during the Paleocene-Eocene thermal maximum overwhelmed this ancient stabilizing system. Imagine those trillions of tons of carbon erupting from the seafloor and filling the sky, now beginning to dissolve relentlessly into the surface waters. As carbon dioxide dissolves in water, it forms carbonic acid. A weak acid, yes, the same one that gives a soft drink its gentle fizz. But when this process happens on a global, geological, and catastrophic scale, that gentle fizz becomes a profound, corrosive, and planetary scale crisis. The ocean began to acidify, and it did so with a speed that the rock record had not seen in millions of years. The consequences for marine life were immediate and devastating, particularly for any creature that built a shell. A wave of extinction, silent and unseen, swept through the deep seas. The hardest hit were the foraminifera, tiny, single-celled organisms that float in the water or live on the seabed, building intricate, beautiful shells from calcium carbonate. These tiny creatures are the foundation of the marine food web. As the water turned corrosive, their shells, the very structures of their bodies, began to dissolve. The fossil record shows a dissolution layer, a stark, dark band in the ocean sediment, where these tiny, calcareous fossils simply vanish. They were, in effect, melted. This was a profound, bottom-up collapse. The very base of the oceanic food chain was being chemically erased. This acidic pulse, combined with the rapidly soaring water temperatures, created a dead zone in the deep. The oceans in this new, superheated greenhouse state likely became stratified and sluggish. The deep waters may have lost their oxygen, becoming vast, anoxic pools, much like in the ancient extinction events. It was, for the deep sea, an apocalypse. And yet, this crisis, this other catastrophe that unfolded in the dark, had a strange, paradoxical, and ultimately crucial effect on the world that was to come. It was part of the Great Reset. It cleared the decks. It was the chaotic chemical furnace that, by eliminating old forms of life, set the stage for the new, warm-adapted marine ecosystems of the Eocene. The planet was now truly in the grip of a global fever. The air was thick and hot, the oceans were acidic and stratified. The old world was gone. This new, extreme and volatile set of conditions, born from this immense geological spasm, was now the new normal. And on land, life, which had been slowly recovering, now had to adapt, and adapt fast, to this new, superheated hothouse world. The true rainforest planet was about to be born from this fever. The fever had taken hold. This new, superheated, carbon-drenched normal, born from the great methane belch, was not just an oceanic crisis. It was a profound atmospheric transformation that rippled across the continents, forcing the terrestrial biosphere, the world of plants and the mammals that had just begun to inherit it, into a period of rapid, chaotic, and revolutionary change. The effects on land were complex, a story not just of universal growth, but also of profound stress, migration, and transformation. The planet was, in essence, being reorganized by heat. Imagine the forests of the Paleocene, those quiet, recovering, temperate woodlands. As the global temperature soared by 5, 6, even 8 degrees Celsius, these established ecosystems were thrown into chaos. For the plants, this was a climate migration, enforced at the speed of a geological sprint. A tree cannot simply get up and walk north to escape the heat. A forest must move, generation by generation, seed by seed, a slow-motion march towards cooler latitudes. As the tropical and subtropical belts, driven by the new heat, expanded aggressively outwards from the equator, they pushed the temperate zones poleward. Forests of oak, beech, and pine, once comfortable in middle latitudes, were now forced to run north or die. Many lineages, unable to disperse their seeds fast enough to keep pace with the rapid, thousand-year warming, likely did die, their populations withering in a heat they were never designed for. This was the brown of the New World, vast regions of stressed, dying, or zombie forests, unable to cope with the sudden new climate. But for other plants, for those adapted to warmth and humidity, this was not a crisis. It was an opportunity, a global, planetary-scale invitation. The tropical rainforests, those vibrant, multi-layered engines of biodiversity, exploded. They surged outwards from the equator, following the heat and the likely increase in global humidity as the warmer oceans evaporated more water. They conquered vast, new territories. What was once a dry, temperate woodland in North America or Europe now became a dense, humid, subtropical jungle. This was the green of the New World. The planet was, quite literally, turning green from pole to pole. The hothouse state, fueled by the super-high carbon dioxide levels, also provided a powerful aerial fertilizer for this new plant kingdom. The forests that grew in this era were perhaps lusher, faster-growing, and more dense than any that had come before. And this great planetary-scale greening was the engine that fueled the next great evolutionary leap. For the small archaic mammals of the Paleocene, this new, super-productive global hothouse was a paradise. The world, for them, had just become a single vast interconnected tropical buffet. This triggered an explosion of diversification and migration. Mammals, which had been slowly, cautiously evolving, now spread across the globe with astonishing speed, following the spread of the forests. The ancestors of modern primates, horses and hoofed animals all appeared and radiated during this hot, fertile time. They were able to cross land bridges, like the ones still connecting Europe and North America via Greenland, that were now, for the first time, warm, forested and hospitable. The Paleocene-Eocene thermal maximum, for all its destructive acidic fury in the oceans, was the forge for the modern age of mammals. It was the heat that broke the old barriers, that created a new, vast green world, and that fueled the evolutionary explosion of our own ancestors. This global fever, this sudden violent planetary realignment, was the event that truly created the rainforest planet. It was the force that would melt the last vestiges of any polar ice and allow those lush, warm, tropical-style forests to begin their most impossible, most uncanny, and most mind-bending migration of all, their journey into the high, dark, and final frontier of the poles themselves. This is perhaps the most profound, most unsettling, and most beautiful secret of the rainforest planet. We must, in our minds, completely erase our modern image of Antarctica. We must delete the picture of a vast, high, white desert, a continent buried beneath kilometers of solid ice, a place of lethal, inhuman cold, and 6-month-long nights of unimaginable, frozen darkness. That Antarctica, the white continent, did not exist. Let us journey south 50 million years ago into the Eocene. We cross the warm southern oceans and we arrive at the coast of the great southern continent. And it is green. Imagine this, a vast landmass, larger than Europe, completely free of any significant permanent ice. Its great mountain ranges, the Transantarctics, are not buried, but are exposed, rocky peaks, perhaps dusted with seasonal snow in the winter, their slopes carved by flowing liquid rivers. The air is not frigid and dry, it is cool, humid and mild. The dominant sound is not the howling of the wind over a frozen plain, but the sound of rain dripping from the leaves of a vast, dense and temperate rainforest. This is not speculation. This is a fact, written in stone in the fossils that have been, with great difficulty, recovered from the few, brief summer exposures of rock that peek through the modern ice sheet. What did paleontologists find here, at the bottom of the world? They found pollen, they found petrified wood, they found fossilized leaves. They found the undeniable, perfectly preserved remnants of a lost, thriving and complex forest. This was not a sparse, struggling, tundra-like scrub. This was a rich, multi-layered, temperate rainforest. The canopy was dominated by trees whose descendants are now scattered across the southern hemisphere. The southern beech, nothofagus, a relative of the beeches and oaks of the north. Alongside them grew tall, stately podocarp conifers, relatives of the modern yellowwoods of New Zealand and South America. Imagine walking through this forest. The light is perhaps dim, filtering through the high canopy of the beeches and conifers. The forest floor is a thick, soft, damp carpet of mosses, liverworts, and, above all, ferns. The air is cool, perhaps, but never, ever freezing. It is a world of endless, gentle, green twilight. This forest, this lost Antarctic kingdom, was not a brief hothouse anomaly. It thrived for millions of years. It supported an ecosystem. We have found the fossils of the animals that lived here. Small, primitive marsupial mammals, perhaps, ancestors of those that would one day colonize Australia. We have found the bones of large, flightless, ratite-like birds wandering the forest floor. The rivers likely held fish and amphibians. It was a complete, functional, and isolated world. This is the true, uncanny ghost of the hothouse Earth, a green, living, breathing continent at the very South Pole, a place of rivers, of forests, of rain, a world that proves with a quiet, profound finality that the Earth's natural state is not necessarily the one we were born into. But this green paradise held one final, almost unimaginable secret, a secret that separates it from any forest on Earth today. It was a forest that, for all its mild, temperate warmth, still had to endure the immutable astronomical reality of its position on the globe. It was a forest that for 3 long, dark months of every year was plunged into the warm, damp, and absolute darkness of the polar night. This is the ultimate, profound, and beautiful paradox of the Antarctic rainforest. It was a world that solved a problem that no ecosystem on Earth today has to face: the challenge of high warmth combined with profound, prolonged darkness. Imagine this forest through its yearly cycle. For the long summer months, the sun, the same distant, low-angle sun that glitters over the ice today, would circle the horizon, never setting. It was a time of 24-hour, continuous, gentle daylight. The forest would burst into a frenzy of activity. The nothofagus trees, the southern beeches, would manage their entire year's worth of growth, their leaves unfurled, capturing the faint, continuous light. The ferns and mosses on the forest floor would thrive in the damp, humid, twilight sun. But then the season would turn. The sun would dip lower, touch the horizon, and finally disappear. And the long polar night would begin. 3 months of cold, continuous, absolute blackness. Yet, it was not cold. The mild, greenhouse-driven climate, the warm ocean currents surrounding the continent, kept the temperatures well above freezing. It was a warm, damp, and pitch-black winter. How did a forest survive this? It did so by adapting in a way that is, for us, deeply counterintuitive. We associate deciduous trees, trees that drop their leaves, with winter, with the onset of cold and frost. But the Antarctic forests, the nothofagus, and perhaps even some of the podocarp conifers, were almost certainly deciduous for a completely different reason. They dropped their leaves not to survive the cold, but to survive the dark. A leaf in the darkness is a liability. It is a living, breathing piece of tissue. It respires. It consumes energy, burning precious sugars to stay alive. But in the dark, it cannot photosynthesize. It cannot produce any new energy. To keep its leaves on in the dark would be, for a tree, the equivalent of leaving every light on in a house during a multi-month power outage. It would be a slow, metabolic suicide. And so, as the long twilight of the Antarctic autumn began, the forests would have put on a silent, spectacular show. The leaves of the nothofagus trees would turn, perhaps, to brilliant yellows, oranges, and reds, not in response to frost, but to the failing light. A vast, colourful, temperate carpet would settle onto the damp, mossy forest floor. For 3 months, the forest would sleep, not in a frozen, death-like hibernation, but in a warm, dark, metabolic stillness. The trees stood as bare, silent skeletons, their buds sealed, their energy conserved, waiting patiently in the humid darkness. The only sounds would be the drip of rain, the gurgle of unseen rivers, and the rustle of the small nocturnal marsupials and birds foraging in the thick, rich, undecayed leaf litter, a feast that would last them through the winter. This was a lost ecosystem, a lost rhythm, a warm, deciduous polar rainforest. It is a world that strains our imagination, a quiet, gentle green world that thrived at the bottom of the earth, its entire existence a beautiful evolutionary solution to a problem of eternal twilight. This green, light-starved and profoundly quiet world defined the South Pole. But the planet is a sphere, and at the very opposite end of the globe, in the high Arctic, an even stranger, warmer, and perhaps even more vibrant jungle was thriving, a place that truly defies all modern logic. We journey now to the top of the world. Our destination is Ellesmere Island, in the high Canadian Arctic, far north of the Arctic Circle. Today, this is a land of almost lunar desolation. It is a world of biting, year-round cold, a polar desert of barren rock, immense glaciers, and a vast, frozen, permanent sea of ice. It is one of the most inhospitable, lifeless places on the modern Earth. But 50 million years ago, in the warmth of the Eocene, this same exact spot on the globe, still located within the Arctic Circle, was unrecognizable. It was not a desert of ice. It was a jungle. Imagine standing on Ellesmere Island then. The air is not frigid and biting. It is warm, soft, and incredibly humid. The landscape is not white and grey, but a deep, vibrant, and almost overwhelming green. You are standing in a dense, lush, swampy forest, a forest that feels almost subtropical. This is not speculation. This, too, is written in the stone. The fossil beds of Ellesmere Island, preserved in the ancient mud of this lost world, have yielded one of the most astonishing floral assemblages ever discovered. The fossils tell a story that seems, to our modern minds, to be an impossible paradox. Paleontologists digging in the now frozen ground have found the fossilized leaves, the petrified wood, and the pollen of a forest that has no right to be there. They found Metasequoia, the dawn redwood, a giant deciduous conifer related to the modern redwoods of California, but one that, unlike them, shed its needles in the winter. They found ginkgo trees, their delicate fan-shaped leaves pressing into the ancient mud. They found relatives of cedars, firs and spruces, but also, astonishingly, broad-leafed trees, relatives of modern sycamores, birches and elms. It was a rich, dense, multi-layered forest, far more diverse and lush than the temperate nothofagus forests of the Antarctic. The climate here was not just mild, it was warm. The Arctic Ocean, which today is a cap of permanent ice, was, in the Eocene, a warm, perhaps almost stagnant body of water, its surface temperature in the summer perhaps reaching 20 degrees Celsius or 68 degrees Fahrenheit. The shores were lined with vast, cypress-like swamps, the air thick with moisture and the hum of insects. This was a warm, temperate, or even subtropical swamp forest, thriving at a latitude where today the sun does not rise for 3 months of the year and the temperature rarely climbs above freezing. This is the Arctic paradox. It is the ultimate expression of the hothouse Earth. It proves that the Eocene fever was so profound, so complete, that it all but erased the very concept of polar cold. The planet's heat engine was in overdrive. The warm ocean currents and the thick greenhouse gas-laden atmosphere working in concert to transport tropical heat all the way to the very top of the globe. And like its Antarctic counterpart, this warm, teeming, swampy jungle had to endure the immutable astronomical reality of its position. It, too, was plunged into the long, dark polar night. Imagine this world in its winter. The sun sets and does not rise again for 3 long months, but the world does not freeze. The air remains warm, humid, misty. The great dawn redwoods, like the Antarctic beeches, drop their needles, not from cold, but from darkness, carpeting the swampy ground in a thick reddish-brown mat. It is a world of warm, wet, and total blackness. This warm, dark, swampy forest, this impossible Arctic jungle, was not an empty, silent stage, populated only by trees. A world this rich, this warm, this fertile, would inevitably be filled with life. And the fossils found on Ellesmere Island, alongside the leaves and the wood, reveal the animals that inhabited this strange polar paradise. They are, if anything, even more baffling, even more paradoxical than the trees themselves. And the animals that inhabited this impossible, warm Arctic jungle are, indeed, the most profound paradox of all. When paleontologists began to sift through the Eocene muds of Ellesmere Island, they found not just the leaves of redwoods and the wood of sycamores. They found the bones, the scutes, the teeth of creatures that, by every law of our modern world, simply should not, could not be there. They found alligators. Let that image settle in your mind. Alligators, the quintessential cold-blooded reptiles, creatures utterly dependent on external heat, on basking in the hot sun to warm their bodies and power their metabolisms. Today their range is defined by a strict thermal line, a frost line, beyond which they cannot survive a cold winter. Yet here, in the high Arctic, at 78 degrees north latitude, paleontologists have found their fossilized bones and their characteristic armored skin plates, or scutes. This was not a stray, lost individual. This was a thriving, breeding population. Imagine it, a large, alligator-like reptile, perhaps a relative of the modern alligator, gliding silently through the warm, dark, swampy waters of an Arctic river, its eyes and nostrils just breaking the surface. It is a creature that has never, in its entire evolutionary history, seen ice. And it was not alone. Alongside the alligators, they found the fossilized shells of large freshwater turtles, other quintessential cold-blooded creatures, needing warmth to digest, to move, to even exist. They found the remains of large tortoise-like animals, suggesting they were walking the swampy forest floor. This was not a reptile-only ecosystem. The mammals were here too, and they were large. The fossils revealed the presence of Coryphodon, a strange, archaic, hippo-like mammal, a bulky, tusked plant-eater, perhaps weighing half a ton, its stout legs perfectly adapted for wading through the soft, wet, swampy ground, browsing on the lush, aquatic vegetation. They found the bones of primitive, tapir-like creatures, and perhaps even early primates, cousins of our own distant ancestors. This was a complete, functioning and warm-blooded and cold-blooded ecosystem thriving year-round within the Arctic Circle. The presence of the warm-blooded mammals like Coryphodon makes a strange kind of sense. They could generate their own body heat. But the alligators, the turtles, the tortoises, they present the ultimate riddle. Their very existence is the definitive, non-negotiable proof of the Eocene hothouse. Their fossils are the ancient thermometers telling us, with a certainty that no climate model can dispute, that the temperature never dropped below freezing, not even in the depths of the long, dark polar winter. And this is the strangest, most difficult, and most wondrous part of the entire story. How did they do it? How did a forest, a rainforest, survive 3 months of total darkness? But even more profoundly, how did an alligator, a creature that lives by the sun, survive a winter, not of cold, but of a warm, humid, and perfectly, absolutely black 3-month-long night? This is the ultimate and most beautiful paradox of the Eocene hothouse. A warm, thriving, complex ecosystem populated by both deciduous forests and cold-blooded alligators existing inside the Arctic Circle, yet forced to endure 3 continuous, lightless months of polar night. How could this possibly work? How did life solve the riddle of a warm, wet but pitch-black winter? The answer, it seems, lies not in resistance, but in surrender. Life, in this impossible forest, adapted by entering a profound, collective and warm, suspended animation. First, the forest itself. We must look again to the dominant trees, the metasequoia or dawn redwood, and the other broad-leafed trees like sycamores. Like their Antarctic cousins, these were almost certainly deciduous. But they were deciduous for a reason that is, to us, deeply alien. They did not drop their leaves in response to the cold. They dropped them in response to the dark. Imagine the long, slow Arctic autumn. The sun circles lower and lower, its weak, slanted light offering less and less energy. The trees, sensing this failing light, begin to prepare. Photosynthesis, the engine that turns light into sugar, becomes impossible. A leaf in the dark is no longer an asset. It is a metabolic drain, a living, breathing mouth that consumes energy but produces none. And so, the forest would let go. In a final, silent, colourful cascade, the needles of the redwoods, the broad leaves of the sycamores, would turn yellow and red and fall, carpeting the warm, damp, swampy ground in a thick, insulating mat. The entire vast Arctic jungle would stand as a forest of bare, silent skeletons, not frozen, but waiting. They entered a state of warm dormancy, their buds sealed, their metabolisms reduced to a mere flicker, a quiet, patient sleep, fueled by the stored sugars of the long, sunlit summer. But what of the alligators, the turtles, the large, cold-blooded reptiles? They cannot drop their leaves. Their very existence is a fire fueled by the sun. How do they survive a 3-month night, even a warm one? They too would surrender. They would enter a state of profound torpor, a warm hibernation. Imagine the scene as the last faint ray of sun vanishes from the horizon. The large alligator, its belly full from the summer's feasting, glides slowly into the deepest, perhaps most stable part of its dark, swampy river. It sinks to the bottom, into the soft, anoxic mud, and it simply stops. Its heart, already slow, would beat even slower, perhaps only once every few minutes. Its breath, its need for oxygen, would drop to almost zero. Its complex reptilian metabolism would shut down, entering a state of profound, suspended animation, living entirely off the immense, rich fat reserves it had built up. It was not hibernating from the cold, it was hibernating from the dark. It was hibernating from the absence of energy. The turtles would do the same, burying themselves in the soft, warm mud. The entire ecosystem for 3 months would be a sleeping world. A warm, dark, and utterly silent forest, its trees bare, its rivers filled with the sleeping, suspended forms of its largest predators, all waiting in a collective, breathless stillness for the first faint returning promise of the sun. This polar paradox, this world of sleeping, warm jungles, was a perfect, strange, and stable solution, a pinnacle of the hothouse Earth. This was the reality at the poles. But the poles were the mildest part of this planet. The true, terrifying, and almost unimaginable engine of this global fever was at the equator, and it was here, in the hottest, wettest, and most fertile part of this new world, that life, now completely unleashed from the shadow of the dinosaurs, would experiment with gigantism on a truly mythological scale. This was the new normal, a world without ice, a planet wrapped in a thick, humid greenhouse blanket, where the very poles were lush, swampy forests. This was the Eocene, the true rainforest planet. And this global, profound and stable warmth was not just a climate curiosity, it was an evolutionary catalyst. It was the fertile, wet and bountiful garden in which the seeds of our own age, the age of mammals, would finally, explosively take root. We must remember the world that came just before, For 165 million years, the mammals, our ancestors, had lived in a state of arrested development. They were small, nocturnal, secretive, living in the literal and figurative shadows of the dinosaurs. They were the mice in a world of dragons, their evolutionary potential held in check by a dynasty of reptilian giants that dominated every significant niche. Then the asteroid fell. The Great Silence. The dinosaurs were gone. The Paleocene, as we saw, was the slow, quiet, cautious recovery. But the Eocene, kicked into high gear by the great carbon-fueled fever of the PETM, was something else entirely. It was not recovery, it was conquest. For the surviving mammals, this new hothouse world was an open, limitless, and perfect paradise. Imagine it from their perspective. The single greatest, most persistent, and most terrifying threat of their entire evolutionary history had been completely, miraculously erased. There were no more tyrannosaurs. There were no more raptors. The night was no longer the only safe time. The ground was no longer a death trap. And at the same time, the world had become a global buffet. The combination of intense, stable warmth, high humidity, and an atmosphere saturated with carbon dioxide, the very food of plants, created a botanical explosion. The rainforests, as we have seen, spread from pole to pole. The planet was perhaps more fertile, more productive, and more green than it has ever been before or since. No predators and infinite food. This was the ultimate evolutionary vacuum, and mammals with their adaptable, warm-blooded and intelligent blueprint rushed in to fill it. The age of mammals truly began here in the Eocene heat. It was an explosion of creativity, a radiation of life, as if a dam had burst. The small, shrew-like survivors of the Paleocene diversified into a bewildering, almost chaotic array of new forms, experimenting with size and diet in ways that had been impossible for 100 million years. Imagine the forests of this ES. They are filled with these new, strange experimental drafts. The first large herbivores, the Uintatheres and Coryphodon, the hippo-like creature of the Arctic, were achieving the size of modern rhinos, browsing on the lush foliage, their bodies protected by bony knobs and saber-like tusks. The first large carnivorous mammals, the creodonts and mesonychids, were evolving to hunt them, becoming wolf-like, hyena-like, or even bear-like, the first mammals to claim the title of apex predator. The first true primates, our own distant lemur-like ancestors, were leaping through the canopy of these global tropical trees. The first bats took to the wing, filling the warm, humid nights. The first horses, tiny, dog-sized creatures, browsed the leafy undergrowth. And in the warm, shallow seas, the first whales, those descendants of land mammals, were returning to the water. This hothouse world was the cradle. It was the time and the place where the blueprints for almost all modern mammal lineages, including our own, were first drawn. But this evolutionary explosion, this riot of new life, was not uniform. The planet, while universally warm, was not the same everywhere. The equatorial regions, the very center of the hothouse, would have been almost unimaginably hot, humid, and fertile. And it is here, in the deepest, most ancient, and most productive jungles of this new world, that evolution, freed from all constraints, would produce its most extreme, most terrifying, and most gigantic first drafts. To see this, we must journey to a place where the rain was constant, the heat was profound, and the rivers were ruled by a new dynasty of giants. We must travel to the lost, swampy river delta of what is now Colombia. This is the hothouse within the hothouse. If the poles were warm, the equator, in this age, was a realm of profound, almost suffocating superheat. The average temperature here may have been a staggering 30, perhaps even 34 degrees Celsius over 90 degrees Fahrenheit. year-round, day and night. And it was wet. Incredibly, unimaginably wet. This was a world before the Andes Mountains had risen to block the weather. A world where moisture from the oceans flowed freely. This was the birthplace of the modern rainforest, but in a form more vast, more lush, and more primal than anything we know today. Imagine not just a river, but a colossal, swampy river delta system. A vast, flat, waterlogged plain, crisscrossed by wide, slow-moving, muddy rivers, not so different, perhaps, from the ancient Chem beds where Spinosaurus once ruled. The air is thick, heavy, almost viscous with humidity. The sky is a pale, milky white, perpetually overcast, the sun a diffuse, oppressive glow. The dominant sound is the constant, deafening, drumming roar of tropical rain falling on a forest of almost unimaginable density. This was a world of botanical gigantism. The plants here, supercharged by the heat, the water, and the incredibly high carbon dioxide levels, grew to colossal sizes. The ancestors of modern palms, legumes, and banana trees formed a dense, towering, closed canopy, a sea of green that trapped the heat and the moisture below. And in this supercharged, hothouse, wet world, the cold-blooded animals, the reptiles, whose body size is so often dictated by the ambient temperature, were unleashed. The warmer the world, the larger they can grow. And in the hottest, most fertile world the Earth had seen in 60 million years, they grew to sizes that were, and still are, truly mythological. The Terrestrial fossil beds are not just a snapshot of a rainforest, they are a snapshot of a world of giants. This was not a balanced ecosystem of large and small. This was a world where everything was immense. Imagine the rivers. They are choked with some of the largest freshwater fish ever known, giants that dwarf modern arowana or catfish, and lurking in the shallows, waiting for them, are colossal, primitive crocodiles. Acherontissuchus, the river of sorrow croc, itself a monster, perhaps 7 meters long, specializing in hunting these giant fish. And on the banks, or perhaps wading in the murky, warm water, is the prey for an even larger predator, Carboniferous, the coal turtle. This was not a small, humble creature. This was a freshwater turtle with a shell over 1.7 meters, nearly 6 feet across. A turtle the size of a small dining room table, its skull the size of a football, its jaws powerful enough to crush the smaller crocodiles that shared its river. This was the world. A hot, wet, swampy kingdom, a world of car-sized turtles and giant crocodiles, all thriving, all growing to colossal sizes in the perpetual greenhouse heat. An ecosystem of almost unbelievable reptilian abundance. This was the prey, this was the larder, and an ecosystem this rich, this hot, this full of giant, armored turtles and massive crocodiles would inevitably, by the cold, evolutionary logic of the arms race, produce a predator capable of hunting them. It would produce an apex predator, a creature that, in this perfect, serpentine, hothouse world, would rise to a level of gigantism that even the dinosaurs had never achieved in its particular form. This swamp was the kingdom of the ultimate, colossal snake. This was Titanoboa cerrejonensis, the titanic boa from Cerrejón. It is, to our knowledge, the largest snake that has ever existed, a creature of such mythological proportions that its discovery in 2009 seemed to pull a beast from the realm of legend into the sober pages of science. We know it primarily from its vertebrae, the very building blocks of its immense serpentine body, and these vertebrae are simply, undeniably, massive. When compared to the vertebrae of the largest snake alive today, the green anaconda, they are so much larger, so much more robust, that they imply a creature of a completely different order of magnitude. Let us try, with a calm mind, to build this giant. Titanoboa was a constrictor, a relative of modern-day boa constrictors and anacondas. but its scale is difficult to process. Conservative estimates, based on those colossal vertebrae, place its total length at over 13 meters or 43 feet. Some suggest it could have reached 15 meters or nearly 50 feet. This is a snake as long as a city bus or a T-Rex. And its weight would have been over a ton, a single, solid, muscular reptile weighing more than a large bison. At its thickest point, its body would have been nearly a meter or 3 feet in diameter. A creature so large it could not have easily moved its own immense rope-like body across dry land. Titanoboa was not a jungle snake, as we imagine one, hanging from trees. It was, like its modern anaconda cousins, a water snake. It was a true river monster, its life spent almost entirely in the murky, warm, slow-moving rivers of this colossal, swampy, hothouse world. The water was its home, its camouflage, and its hunting ground. It was the only medium that could support its 1-ton mass, allowing it to move with a silent, fluid, and terrifying grace. Imagine it lying in the warm, muddy shallows of that ancient river, its immense, patterned body almost perfectly submerged, indistinguishable from a large fallen log. Only its eyes and nostrils, perhaps, would break the surface, waiting, with a patience that only a cold-blooded predator can truly possess. And its prey, the very giants that filled this river of monsters. This 1-ton snake was the undisputed apex predator of the most dangerous river on Earth. It hunted the hunters. It ate the Acherontissuchus, the 7-meter-long crocodiles, its relatives. It was one of the few creatures, perhaps the only creature in this ecosystem, capable of preying upon the car-sized, 6-foot-wide Carboniferous turtles, perhaps ambushing them from below and applying the slow, inexorable, and truly irresistible force of its constriction. Imagine that power. A body, a meter thick, made of pure solid muscle, coiling around its victim, not crushing it, but squeezing. A slow, patient hydraulic press, tightening with every exhalation of its prey until the breath and the life, simply, quietly, stops. This was the king of Terrestrial, and its very existence was a direct consequence of the hothouse world. A cold-blooded reptile's size is fundamentally limited by the ambient temperature of its environment. Its metabolism, its ability to digest, to move, to live, is a fire fueled by the sun. To power a 1-ton, 50-foot snake, the environment itself must be a furnace. The 34 degrees Celsius average of the serene jungle was not just a backdrop. It was the engine that allowed evolution to build a serpent of such titanic proportions. Titanoboa was a monster, yes, but it was a monster of its time. It was the ultimate, logical, and perhaps inevitable expression of life in a world of profound, unrelenting, and fertile heat. It was the true serpentine king of this equatorial furnace. But this hothouse world was not all equatorial swamp. This global fever, this rainforest planet, extended its green, humid, and nurturing arms across the entire globe, creating vast, new, milder forests. And it was in these other jungles, these quieter, perhaps cooler but equally lush, European and North American forests, that the other, smaller, and perhaps more familiar survivors of the Great Extinction were beginning their own, equally profound, evolutionary journey. But before we travel to those gentler mammalian worlds, we must remain for one moment longer in the terrifying, superheated furnace of the Terrestrial. Titanoboa, the colossal serpent, was the undisputed apex predator. But it was not the only giant. An ecosystem that can support a 1-ton snake must be, itself, a world of monsters. The river was a chaotic stage, and the titanic boa was not the only player. It was surrounded by its neighbors and its prey. The heat of this Paleocene equator, this river of giants, was a powerful evolutionary engine for all cold-blooded life. It did not just forge a giant snake, it forged giant prey and giant competitors. The entire food web was locked in a high-temperature, high-stakes arms race of gigantism. Let us picture the other inhabitants of this murky, warm, swampy river. Lurking in the same waters, navigating the same channels as Titanoboa, was Acherontissuchus, the river of sorrow crocodile. This was a dinosaur, a member of an ancient and now extinct lineage of crocodile relatives, many of which were marine. But this one was a freshwater specialist, and it was a giant in its own right, perhaps reaching 7 meters, over 20 feet, in length. It was a powerful, long-snouted predator, its jaws lined with sharp, slender teeth, perfectly adapted for its primary diet, the colossal fish that teemed in this river. Acherontissuchus was, perhaps, the underboss of this river. It was a formidable hunter, likely preying on anything smaller than itself. But in a world patrolled by the 50-foot Titanoboa, it was also tragically on the menu. It was both hunter and hunted, a giant living in the shadow of an even greater giant. But this river system hosted another creature, a creature so large, so formidably armored that it may have been one of the few things Titanoboa could regularly and safely prey upon. This was Carboniferous, the coal turtle. Imagine a freshwater turtle. Now imagine it scaled up to the size of a small car, like a Volkswagen Beetle. This is not an exaggeration. Carboniferous possessed a shell over 1.7 meters, nearly 6 feet, across. It was a true, round, walking tank. Its skull was the size of a regulation football, massive and powerful, with immense hooked jaws that, paleontologists speculate, were powerful enough to crush the smaller crocodiles that shared its water. It was an omnivore, perhaps, but a formidable, aggressive one. This car-sized, armored turtle, this was the prey. This is what completes the picture of this lost hothouse world. Titanoboa became a 1-ton, 50-foot monster, not just because the heat allowed it, but because its food source required it. To hunt and kill a creature as large, as powerful, and as impenetrably armored as a Carboniferous, a predator must evolve to an almost mythological scale. It required the slow, inexorable, and truly irresistible crushing power of a 1-ton constrictor. This was the law of the Terrestrial, a self-contained hothouse world of reptilian giants, a brutal, scaled-up echo of the long-gone Mesozoic, an evolutionary experiment in heat and scale. But this equatorial, superheated furnace was not the only story of the Eocene. The global fever, this rainforest planet, also created, as we've noted, vast, milder, gentler jungles across Europe and North America. And it was in these quieter, perhaps cooler, but equally lush forests, far from the terror of Titanoboa and its giant reptilian neighbors, that a different and ultimately more significant evolutionary story was unfolding. The small mammalian survivors of the Great Extinction were, in these safe havens, beginning their own quiet and profound journey. Let us now leave that terrifying reptilian hothouse of giants behind. We travel from the equatorial furnace of Terrestrial to the other rainforests of this planet, the quieter, perhaps gentler, but equally lush jungles that, in the Eocene, covered what is now Europe and North America. Here, in the warm, dappled light, a different evolutionary story was unfolding, one not of monstrous scale, but of quiet, humble, and familiar beginnings. Imagine yourself in a dense, warm, and humid forest. This is the world preserved in the famous Messel Pit in Germany, or the Bighorn Basin of Wyoming some 50 million years ago. It is a subtropical jungle, a world of broad-leafed trees, climbing vines, and a thick, rich undergrowth of ferns and soft shrubs. The air is still, heavy with the scent of damp earth, flowering plants, and rotting fruit. Moving almost silently through this dense, cluttered forest floor is a creature. It is small, shy, and utterly unassuming. At a first quick glance, you might mistake it for a small deer or perhaps a fox. It stands barely 30 centimeters, a single foot, tall at the shoulder. It has an arched back, a relatively short neck, and a small, delicate head. This tiny, timid creature, browsing nervously on the softest, tenderest leaves and fallen fruit, is the ancestor of the horse. We call it Eohippus, the dawn horse, or perhaps more accurately, Propalaeotherium. It is a perfect, beautiful illustration of how profoundly evolution can transform a lineage, of how the grandest forms can arise from the humblest, most unrecognizable beginnings. Let us look closely at this dawn horse. It is not built for running across open plains. It is built for navigating the cluttered, tangled, soft-floored jungle. Its feet are the most telling clue. It does not stand on a single, strong hoof. Instead, its front feet possess 4 distinct, splayed-out toes, each ending in a tiny, individual nail-like hoof. Its hind feet possess 3. These multi-toed feet were perfect for walking quietly on the soft, damp forest floor, spreading its small weight, preventing it from sinking into the mud. Its teeth are not the great, grinding, high-crowned mills of a modern horse, designed for chewing tough, abrasive, silica-rich grasses. Grasses, as we know them, barely existed yet, or were not widespread. Eohippus was a browser. Its teeth were small, low-crowned, and bumpy, perfectly adapted for its soft, gentle diet. The tenderest new leaves, the soft buds of ferns, and the sweet fallen fruits of the hothouse forest. Imagine its life. It is a creature of the shadows, of the deep undergrowth. Its small size and perhaps dappled or striped coat, like that of a modern fawn, would provide perfect camouflage in the filtered jungle light. It is a solitary animal, or perhaps lives in small, quiet family groups. Its entire existence is one of stealth. Its ears are constantly swiveling, listening for the faint snap of a twig, the signal of a predator. This could be the giant, flightless bird Gastornis, or a primitive, cat-like creodont, the new hunters of this mammalian world. This tiny, 4-toed, fruit-eating, forest-dwelling creature, this shy ghost of the Eocene jungle, seems a universe away from the animal we know today. The large, powerful, single-hoofed, grass-eating, herd-living equus that thunders across the open plains. And yet, this is where that grand lineage began. It started in the warm, stable, nurturing cradle of the rainforest planet. This global hothouse, this world of endless, interconnected forests, was a safe, fertile garden that allowed these first, humble experiments to take root and thrive. It was a world of opportunity, a new Eden, unfolding in the deep, fertile and silent undergrowth, while another, equally vast and unexplored realm, the sprawling sunlit branches of the canopy, waited just above, offering its own, unique set of possibilities. And in that vast, new sunlit kingdom, the canopy of the global Eocene rainforest, a different kind of mammal was beginning its own quiet, evolutionary journey. High above the tiny, browsing horses and the dangers of the forest floor, these creatures found a new world, a 3-dimensional arboreal paradise. These were the first true primates, the distant, ancient, almost unrecognizable ancestors of monkeys, apes, and ourselves. Imagine the Messel pit in Germany, again, that perfect 50-million-year-old snapshot of the Eocene jungle. Here, amongst the fossilized leaves and ancient fish, scientists found a small, exquisitely preserved creature, Darwinius massillae, nicknamed Ida. It is a fossil of breathtaking completeness. Its tiny skeleton, its fur, even the faint outline of its last meal, preserved in the fine oil shale. Let us look at this ghost from our own deep past. It is not a monkey. It is not a human. It is something far more primitive, something close to the great divergence, resembling perhaps a modern lemur, but with its own ancient features. It is small, perhaps the size of a squirrel, with a long balancing tail. Its hands and feet are the key. They are not the paws of a dog or the hooves of Eohippus. They are grasping hands. They possess opposable thumbs and big toes, perfect for gripping the slender branches of the hothouse jungle. Its eyes are large, its snout relatively short, suggesting a life that was beginning to rely more on vision and less on smell. This was the primate blueprint forged in this warm, arboreal world. This global pole-to-pole rainforest was the perfect, uninterrupted highway for these small, climbing creatures. Imagine them, leaping from branch to branch, moving through a canopy that stretched perhaps across entire continents, from North America to Europe, across the warm, forested, high-latitude land bridges. Their life was one of agility, of three-dimensional awareness, and perhaps of a new kind of diet. Their simple teeth suggest they were omnivores, feeding on the bounty of the canopy, the new, abundant flowers, the sweet, soft fruits, the countless insects. They were the generalists of the treetops. This was our own humble beginning. Our entire lineage, the one that would 50 million years later produce a mind capable of contemplating the stars, began here as a small, lemur-like fruit-eating creature, hiding in the leaves of a jungle that was, itself, a temporary hothouse dream. The warm, stable and boundless forest of the Eocene was our cradle. It selected for the very traits that would come to define us: grasping hands, sharp, forward-facing, color-discerning eyes, and a brain, perhaps, that was becoming increasingly adept at navigating a complex, three-dimensional social world. Picture these tiny, agile ancestors. They are quick, watchful, living in a world of abundant opportunity, but also one of new, strange dangers. Their large eyes scan the canopy, not just for the next ripe fruit, but for the shadow of a predatory bird or the silent, serpentine movement of a snake along the branches. Their world was the canopy, a realm of light and leaves. But they were also undoubtedly aware of the world below them, the dark, damp forest floor. A realm they perhaps visited only fleetingly, a place of different shadows and different, much larger and far heavier footsteps. For the mammal was not the only heir to the dinosaurs' throne. The birds, their only living descendants, were also experimenting with gigantism in this new green world, and one of them had become the undisputed, terrifying ruler of the forest floor. Indeed, the dark, humid floor of the Eocene rainforest was not a safe place. While our tiny, primate ancestors ruled the high canopy and the dawn horses browsed the undergrowth, the role of the apex predator, the top-level carnivore in many of these new, post-dinosaur ecosystems, was not immediately filled by a mammal. It was claimed by a descendant of the dinosaurs themselves, a bird. Imagine standing in that German or North American forest 50 million years ago. You hear a sound, not a roar or a growl, but a heavy, deliberate, two-legged thud. A sound like a giant, heavy drum walking through the forest. And then, emerging from the dense ferns, is a creature of almost mythological proportions. This is Gastornis, the terror bird of the Eocene. Picture this animal. It is immense, standing over 2 meters, nearly 7 feet, tall as the largest modern ostriches, but built on a scale of almost unbelievable robustness. Its body is massive, heavy-boned, powerful. Its legs are thick, strong, pillar-like, ending in large four-toed feet, clearly designed to support a great weight. Its wings are tiny, vestigial, almost comically small, tucked uselessly against its broad feathered body. This creature was utterly, completely flightless. But it is the head and neck that truly inspire a sense of quiet, primal awe. The neck is thick, muscular, supporting a skull that is simply enormous, as large as that of a horse, but shaped with a terrible, efficient biological purpose. The beak is colossal, a deep, thick, hooked, razor-sharp weapon, reinforced with bone, a tool that seems purpose-built for crushing, cleaving, or shearing. For well over a century, Gastornis, once known as Diatryma in North America, was the undisputed poster child for the killer bird. Paleontologists looked at that beak, that size, that power, and saw, without question, the apex predator of its age. They pictured it stalking the tiny four-toed horses, the small lemur-like primates, the other mammals of the forest floor. They imagined that immense beak striking downwards, like a battle axe, crushing the skulls of its prey, or shearing off limbs in a single catastrophic bite. It was the nightmare of the Eocene, the dinosaur's ghost, returned to rule the new age of mammals. And yet, in recent years, this terrifying, violent image has been quietly and profoundly challenged. A new story has emerged from the silent chemical whispers of the bones themselves. Scientists, analyzing the calcium isotopes within the fossilized bones of Gastornis, found a chemical signature that did not match that of a high-level carnivore. It matched, instead, the signature of a herbivore, an animal that got its nutrients not from meat, but from plants. This discovery has thrown our understanding into a state of beautiful, contemplative confusion. Was this giant, axe-beaked, terrifying creature a vegan? The image shifts. The beak, so seemingly perfect for tearing flesh, is re-examined. Perhaps it was, instead, a colossal seed cracker, a nut and bolt cutter designed to shear through the immense, rock-hard seeds and tough, fibrous rinds of the exotic hothouse rainforest fruits. Perhaps it was used to dig for large, starchy tubers, or to rip tough bark from trees. Imagine the creature now, not as a silent, stalking killer, but as a giant, peaceful, perhaps communal forest dweller. A 2-meter-tall, flightless parrot moving slowly through the undergrowth, its massive, powerful beak carefully, almost delicately, dismantling the tough defenses of the forest's giant fruits. This, too, is a form of strangeness, a creature that evolved the very shape of a super-predator, but used it, perhaps, for the peaceful act of eating plants. The debate is not settled. Some scientists still argue the evidence points to predation, or perhaps an omnivorous diet, but the very existence of this ambiguity is part of the creature's magic. Gastornis was, regardless of its diet, a true giant of the hothouse world. It was a testament to the evolutionary explosion of the birds, proving that they too were capable of seizing the vacant niche of large terrestrial animal, competing directly with the rising mammals, and for a time producing forms that were larger and perhaps more intimidating than any of their mammalian neighbors. It was another magnificent and ultimately failed experiment. The terror birds, both in Europe and later in the Americas, would eventually fade, replaced by the rising, efficient, predatory mammals. But for a few million years, in the warm, quiet, humid dawn of our age, the forest floor belonged to them. This hothouse world was a time of evolutionary opportunity, a vast global garden. It forced life to experiment. It produced giant reptilian snakes in the equatorial swamps. It produced tiny four-toed horses and agile, grasping primates in the temperate jungles. It produced giant, axe-beaked birds to rule the forest floor. The land was a vibrant, chaotic, and creative laboratory. And at the very same time, this same evolutionary explosion, this same relentless push into new, empty niches, was spilling over back into the one realm that had been for 65 million years emptied of its own giants, the warm, bountiful Eocene Sea. This new, warm, global hothouse, this world of endless pole-to-pole rainforests, was defined by the ocean that sustained it. The seas of the Eocene were vast, warm, and for the first time in over 100 million years, they were empty. The great extinction that had erased the dinosaurs from the land had also, just as completely, erased the great reptiles from the sea. The mosasaurs, the plesiosaurs, The rulers of the Cretaceous deep were gone. The throne of the apex predator of the ocean was vacant, and into this vast, quiet and bountiful void, life, which was exploding with such creativity on land, now spilled over. The new masters of the planet, the mammals, began a journey that seems, to us, almost impossibly strange. They began to return to the water. The story begins on the shores of the ancient Tethys Ocean, perhaps in what is now Pakistan. Imagine a creature, not a whale, but a small four-legged terrestrial mammal, perhaps resembling a strange hoofed wolf or hyena, like Pakicetus. It lives on the banks of a freshwater river, hunting perhaps for fish, wading into the shallows. It is a land animal, but its life is tied to the water, a world of abundant food and few competitors. This first tentative step was the beginning of an evolutionary cascade. Over just a few million years, a geological instant, this lineage committed itself to the deep. We find the fossils of Ambulocetus, the walking whale. Imagine a creature like a furry mammalian crocodile, its hind legs large and powerful, its body capable of undulating, otter-like, through the water. It could still, perhaps, haul itself awkwardly onto the land, but its true home was the aquatic realm. It was a perfect, terrifying, transitional form, an ambush predator of the estuaries. But evolution pushed further, severing the last ties to the terrestrial world. The nostrils drifted back towards the top of the head. The front limbs streamlined into flippers. The body became sleek, powerful, hydrodynamic, and the hind legs, their purpose now gone, began to shrink, to vanish, becoming tiny, useless internal vestiges. This journey culminated in the true global giant of the Eocene seas, the creature that perfectly represents this new Mammalian dynasty. We have met its ghost before, in the dry Saharan valley of the whales, Basilosaurus, the king lizard that was not a lizard at all. This was a 60-foot, serpentine, air-breathing, warm-blooded predator. Its skull was full of sharp, differentiated mammalian teeth. It was the new apex predator, replacing the cold-blooded mosasaurs with a new kind of warm, intelligent, and relentless hunter. It was the new king of the sea, and hidden deep within its sleek aquatic form, it carried the ultimate secret of its origin. Those tiny, perfect, useless vestigial hind legs, the undeniable anatomical ghost of the Eocene rainforest floor, the memory of the land it had left behind. This, then, was the rainforest planet, 50 million years ago, a world of impossible hothouse completeness. It had tiny four-toed horses and agile grasping primates in its jungles. It had giant axe-beaked birds ruling its forest floors. And it had these new, strange, serpentine, warm-blooded whales, the descendants of wolves, ruling its warm, global oceans. The mammal, in its quiet, explosive, post-dinosaur radiation, had conquered all realms. This world, this perfect, green, hothouse equilibrium, seemed like it would last forever. But the Earth, in its slow geological patience, is never truly still. The very climate that had created this paradise, the climate of the Great Fever, was itself subject to new, strange and subtle forces. A new biological process was about to begin, one that would, ironically, use life itself to begin the long, slow cooling, the final fall of the rainforest planet. The Earth was in a profound, stable, hothouse state. The PETM had released a colossal spike of carbon, and the planet's climate had settled into a new, warm equilibrium, a rainforest world from pole to pole. But a system this complex is never truly stable forever. And the force that began the long, slow, 50 million year journey out of this fever, the first gentle push that started the long cooling, may have come not from a geological cataclysm, but from the quiet, insidious, and collective action of one of the smallest, humblest, and most unassuming plants on Earth. This is the story of the Azolla event. It is a beautiful, almost poetic, scientific hypothesis, a testament to the fact that life itself can, in its vast, collective power, fundamentally alter the planetary climate. Let us return in our minds to the Eocene Arctic Ocean 50 million years ago. We have pictured it as a warm, perhaps almost stagnant sea, its shores lined with swampy redwood forests. But this ocean was, at the time, almost completely landlocked. The gaps connecting it to the vast Pacific and Atlantic were narrow, shallow, and restricted. It was, in effect, the largest freshwater, or perhaps brackish water lake on the planet. Imagine this vast, warm, high-latitude body of water, receiving an immense, constant, nutrient-rich runoff from the surrounding rivers that drained the warm, forested continents. And in this warm, nutrient-rich and perhaps stable, low-salinity surface layer, a tiny, floating freshwater fern began to bloom. Its name is azolla. We still have it today. It is a tiny, moss-like, green or reddish plant that floats on the surface of quiet ponds and ditches. It is one of the fastest-growing plants on Earth, and it has a unique symbiotic superpower. It harbors within its leaves a tiny cyanobacterium that allows it to pull nitrogen, the ultimate fertilizer, directly from the air. It is a self-fertilizing, explosively fast-growing photosynthetic machine, and in the perfect, warm, nutrient-rich, high carbon dioxide freshwater pond of the Eocene Arctic Ocean, it went wild. Imagine this, a bloom not of algae, but of this tiny green-red fern, starting in the river deltas and spreading unchecked across the entire surface of the Arctic Ocean. A single, vast, continental-scale mat of living vegetation, perhaps kilometers thick, choking the surface from shore to shore. For 800,000 years, perhaps, this azolla event persisted. In the long 24-hour sunlight of the Arctic summer, this mat would photosynthesize at an unbelievable rate, a colossal green-red sponge, drinking in the immense quantities of carbon dioxide from the hothouse atmosphere, building its tiny, leafy bodies. And then the polar winter would come, the 3 months of warm, total darkness. In the dark, the azolla could not survive. The vast mat would die, and crucially, it would sink. It would rain down in a black organic torrent to the bottom of the deep, stagnant, and perhaps oxygen-free Arctic basin. And there, in the cold, anoxic mud, it was trapped. It did not rot, it did not decay, it was simply buried. The vast, stolen load of atmospheric carbon captured by the tiny plant was sequestered, layer by layer, in the ocean sediment, removed from the planet's atmosphere permanently. Imagine this cycle, repeating summer after summer, winter after winter, for 800,000 years. A relentless, biological, carbon-pumping machine, drawing down the planet's greenhouse blanket, one tiny, dead fern at a time. This, the hypothesis suggests, was the first gentle push. This colossal biological sequestration event may have been the very thing that broke the back of the Eocene fever. By drawing down so much carbon, it thinned the greenhouse blanket just enough, cooled the planet just a few critical degrees, and allowed the first hesitant permanent ice to begin to form at the poles, tipping the Earth out of its hothouse state and into the long, slow icehouse trajectory that would lead to our modern world. It is a beautiful thought, a global climatic fever cured by a tiny, humble fern. But this gentle, biological pull, as elegant as it is, was likely not the only or even the most powerful force at play. As this green living pump was at work in the north, the planet's entire deep geological plumbing, its tectonic plates, were also in motion, grinding slowly towards a new configuration. A configuration that would, far more brutally and far more permanently, rip the world's thermostat out of the wall and leave the southern pole in a state of profound and irreversible isolation. The true, final, and irreversible end of the rainforest planet was not, in the end, a biological story. It was a story of geology, a story of plate tectonics, a story of the slow, grinding, and inexorable movement of the continents themselves. The fever of the Eocene, whether gently cooled by the azolla ferns or not, was ultimately broken by the planet's own deep internal movements, a slow-motion re-engineering of the entire globe. Let us return our gaze to that vast, green, forested continent at the bottom of the world, Antarctica. For millions of years during the Paleocene and Eocene, it had enjoyed a mild, temperate climate. But it was not, at that time, an island. It was the great southern anchor of the world, still connected, or at least in very close proximity, to its two nearest neighbors. A vast forested land bridge, or at least a chain of islands, still linked it to a primitive South America. And to its other side, the continent of Australia was nestled closely against it, the two land masses forming a single, vast southern supercontinent, a remnant of the old Gondwana. This connection was everything. This geography was the key to Antarctica's warmth. Imagine the ocean currents of this hothouse world. Warm, tropical water from the equator flowed southwards, down the coasts of South America and Australia. When it reached the Antarctic landmass, it was deflected. It could not pass through. It was forced to turn, to swirl around the coasts, bringing its life-giving, tropical warmth with it. It was like a giant, planetary-scale hot water system, constantly bathing the southern continent in a mild, temperate, humid embrace. This is what kept the Nothofagus forests alive. This is what kept the ice at bay. But the tectonic plates never rest. Deep beneath these continents, the mantle churned, and the rifting that had begun in the age of dinosaurs continued its slow, patient, and relentless work. First, Australia began to break free. Slowly, millimetre by year, a rift opened between Antarctica and Australia. It widened from a shallow inland sea into a true, deep oceanic passage. Australia began its long, solitary northward drift, the journey that would, millions of years later, carry it to its current position in the warm, tropical latitudes. And then, slightly later, the second and more critical connection was severed. The bond between the Antarctic Peninsula and the southern tip of South America finally, definitively tore apart. The Drake Passage, that notoriously violent stretch of water, was born, opening a gap, a channel, between the southern Atlantic and the southern Pacific. This was the Great Divorce. This was the moment, unfolding in geological slow motion over millions of years during the Eocene, that the Antarctic continent, for the first time in its long, complex history, was left utterly, completely, and permanently alone. It was now an island, a colossal, continent-sized island, sitting in isolation, centered almost perfectly on the South Pole. This profound, new geographic isolation was, in itself, a dramatic change. It cut off the ancient migratory land routes for the marsupials and other life. But its true, world-altering consequence was not on the land. It was in the water. The barriers were gone. The great continental dams, South America and Australia, which had for eons blocked the ocean's flow, deflecting warm water southwards, were no longer in the way. The ocean, for the first time, now had an open, uninterrupted, and circular pathway, a racetrack that looped entirely around the bottom of the world, surrounding the newly isolated Antarctic continent. This new open seaway would not just change a local current. It was about to give birth to the most powerful, most important, and most destructive planet-chilling ocean current of all, the Antarctic Circumpolar Current. And with its birth, the long, warm, green dream of the hothouse Earth was about to be plunged into a deep and permanent freeze. This new open seaway between Antarctica, South America, and Australia was the final fatal piece of the puzzle. The winds of the high southern latitudes, the roaring 40s and furious 50s, which had for eons crashed uselessly against the flanks of continents, were now, for the first time, unleashed. Imagine these winds blowing relentlessly across a stretch of open water that now encircled the entire globe. They pushed the surface water, and that water, with no land to stop it, with no continents to deflect it, began to move. It accelerated, it organized. Over thousands of years, this steady planetary-scale wind in this new, open, circular racetrack gave birth to a phenomenon, the Antarctic circumpolar current. It was, and still is, the largest, most powerful ocean current on Earth. A colossal, cold river circling the entire planet, a river larger than all the world's land rivers combined, flowing forever in a great, clockwise gyre around the southern pole. This current was not just a river, it was a wall. It was a thermal barrier. Before this, the warm, subtropical currents from the equator, from the Pacific and the Atlantic, could flow south, branching off, carrying their life-giving tropical warmth to the very shores of Antarctica, keeping the Nothofagus forests alive. But now, this new, immense, circular cold water current stood in the way. The warm currents flowing south would hit this spinning, fortress-like wall of cold water and be deflected. They were turned back northwards, unable to penetrate the ring. Antarctica, the continent, was now trapped inside this rotating thermal prison. It was, for the first time, completely, utterly, and permanently thermally isolated from the rest of the planet's warmth. The great global hot water pipes that had kept its hothouse running for millions of years had been definitively and geologically severed. The continent was now alone, a prisoner of its own new polar geography, surrounded by a high-speed moat of cold water centered perfectly on the South Pole. It was now a world that lost heat constantly to the cold, dark polar winters, but received almost no heat in return from the global ocean. The great Eocene fever, the global hothouse warmth, was broken. The planet's climate system had found its new, powerful off switch, and for Antarctica, locked in this cold, dark, profound isolation, the long, slow, irreversible freeze was, at last, ready to begin. The isolation was complete. The new, relentless Antarctic circumpolar current, that vast spinning moat of cold water, now circled the southern continent, a perfect thermal prison. The warm, life-giving subtropical currents were gone, deflected, turned back northwards, their heat forever banished from the polar shores. Antarctica, the great green forested continent, was now alone, centered on the South Pole, and exposed, for the first time in tens of millions of years, to the true deep cold of its own orbital winter. The change was not instantaneous. It was a slow, agonizing, and irreversible descent into a new state of being. Imagine the climate of this newly isolated land. The winds that once brought mild, humid, rain-bearing air from the warmer oceans now brought only a biting, sharp, and increasingly cold chill, born from the surface of the new, frigid, encircling current. The continental interior, vast and high, far from any moderating oceanic influence, began to cool dramatically. The seasons, once just a gentle cycle of 24-hour light and 24-hour warm darkness, now took on a new, lethal character. The winter, that long 3-month night, was still dark, but for the first time, it was also cold. In the high interior mountain ranges, the transantarctics, the precipitation that had always fallen as temperate rain, now, for the first time in an age, began to fall as snow. And in the long, dark polar winter, this snow, for the first time, no longer fully melted during the brief, cool summer. Year after year, century after century, the snow accumulated. It piled up, meter by patient meter, its own immense weight compressing the layers below. transforming the soft, airy flakes into hard, dense, granular fern, and then, finally, into the deep, blue, and incredibly heavy ice of a true glacier. This was a sight the Earth had not seen in this region for 50 million years. The first permanent alpine glaciers were being born, small frozen rivers beginning to creep, slowly, ponderously, down the high mountain valleys, scouring the rock that had, for an age, known only the touch of rain and the roots of trees. And this was the trigger for a new, powerful, and relentless feedback loop. Ice is not just cold, it is white. This new, growing, brilliant white surface, the albedo effect, acted as a colossal, continent-sized mirror. The faint, low-angle polar sunlight, which the dark green forests had once absorbed, was now reflected, uselessly, back into space. The more the ice grew, the colder the continent became, and the colder the continent became, the more the ice grew. For the great, warm, deciduous forests of Nothofagus and the podocarps, this was an enemy they could not fight. They had survived the darkness. They had adapted to the long, warm winter. But they had no defense against this. They had no defense against frost. The delicate, living tissues of the trees, the roots, the seeds, were not built for freezing. The death of the Antarctic rainforest was a slow, agonizing, poleward creeping tragedy. The forests in the high interior were the first to die, their skeletons swallowed by the advancing, grinding ice. The great coastal forests, still clinging to the last faint warmth of the sea, held on for perhaps a few million years, a narrow, green, embattled ribbon, besieged by the new, white, silent death from the interior. But they too eventually succumbed. The last Nothofagus tree dropped its last autumn leaf, and the frost crept in. The green was gone. The small alpine glaciers, starved of any warmth, now merged. They flowed together, coalesced, became a single, vast, high-altitude ice cap. This cap grew, thickened, became a dome, an immense, heavy, solid white shield, kilometers thick, spreading outwards from the mountains, burying the dead forests, burying the valleys, burying the entire vast continental landscape under its own colossal frozen weight. This was the birth of the Antarctic ice sheet. This was the moment, unfolding in slow motion over millions of years, that the white continent we know today was born. This event, this final permanent freezing of the southern pole, was not a quiet, local, Antarctic affair. The birth of a continent-sized reflective refrigeration unit at the bottom of the world was a global planetary cataclysm. The deep cold water now pouring off this new frozen continent began to chill the entire planet's oceans from the bottom up. The hothouse fever was not just broken, it was being replaced by a permanent, profound planetary chill. The world as a whole was about to enter a new cold age, and the lush global rainforest planet of the Eocene was, at last, beginning to fade. This new global planetary chill, born from the freezing of the southern pole, was the definitive end of the Eocene dream. The planet's climate system had been fundamentally and irreversibly altered. The long, 50-million-year-old fever which had sustained the rainforest planet had finally, definitively broken. The world as a whole was now tipping, slowly but with gathering momentum, out of the hothouse state and into a new, cooler, and far more dynamic era. This was the dawn of the icehouse world, the world we, in our own time, still inhabit. This was the great cooling. The transition from the Eocene to the Oligocene epoch, around 34 million years ago, was marked by this profound, planet-wide drop in temperature. The world's thermostat, once jammed on high, was now turning sharply, inexorably downwards. Imagine the effects of this new global cold rippling outwards from the freshly frozen Antarctic. The warm tropical and subtropical belts, which had once stretched almost from pole to pole, began to shrink, retreating year by year back towards the equator. The vast, humid, swampy forests of the high latitudes, the very ones that had hosted alligators and turtles in the Arctic and deciduous beaches in the Antarctic, could no longer survive. The cold was a new, slow, invisible and lethal poison, a force their warm-adapted biology could not fight. The rainforest planet, that single, unbroken global biome, began to fragment and die. The change was profound. In the northern hemisphere, the warm cypress-like swamps of Ellesmere Island vanished, replaced slowly by hardy, cool temperate forests, and then, eventually, by the sparse frozen tundra we see today. In Europe and North America, the lush subtropical jungles that had cradled the tiny Eohippus and the first primates began to thin. The broad-leafed evergreen trees gave way to new, tougher, more resilient types of vegetation. This was not a death so much as a transformation. As the global rainforests retreated, new, vast landscapes opened up for the first time in millions of years. The world became perhaps less uniformly green, but more varied, more seasonal. In the mid-latitudes, the familiar deciduous forests we know today, forests of oak, maple, beech and birch, began to spread, their brilliant autumn color cycle a new evolutionary invention, a direct adaptation to this new seasonal cold. And even more critically, in the interiors of the continents, in the rain shadows of rising mountains, the new, cooler, and now drier climate gave rise to a revolutionary new kind of plant, a new ecosystem that would one day conquer the world: grass. The vast open rolling plains, the savannas, the steppes, the prairies. These landscapes, which define so much of our modern planet, were born from the death of the hothouse rainforest. This was the long, slow fall of the rainforest planet. It was a retreat, a fading of the global, humid green, a cooling that would, over the next 30 million years, continue in fits and starts, culminating in the familiar Pleistocene ice ages, the world of woolly mammoths and our own human ancestors. This great planetary cooling was, in essence, a new, profound evolutionary filter. The creatures that had been so perfectly adapted to the stable, endless, hot, wet jungle of the Eocene now faced a new, profound and existential challenge. The world was changing, becoming colder, drier, more seasonal. The food was changing, from soft jungle leaves to tougher, more abrasive grasses. The strange, archaic, experimental mammals of the hothouse dawn, the giant Gastornis birds, the hippo-like Coryphodon. Many of these lineages, perhaps too specialized for the warmth, began to falter and fade, replaced by new, hardier, more adaptable creatures. The age of the rainforest planet was ending, but the legacy of that warm, fertile, 50-million-year-long summer was not erased. It was, in fact, the very foundation of the new world that was to come. The evolutionary explosion of mammals, the diversification of all the great modern lineages that had already happened because of the hothouse, the creatures that would now adapt to and conquer this new, cooler world. The horses, the primates, the whales, the carnivores were all the direct, fortunate children of that long, green and ancient fever. We who live in a world defined by ice at its poles and vast open plains are the direct, fortunate children of that long, green and ancient fever. The Eocene hothouse, that 50-million-year-old rainforest planet, may seem like a strange, distant and alien chapter. It is a world of polar jungles and crocodile-haunted swamps, a world that vanished long ago. But it was not a failed state. It was not an anomaly. It was, perhaps, the single most important evolutionary cradle for the world we know today. We are its legacy. The entire modern age of mammals was forged in that global, equitable warmth. Think of the small, shivering, nocturnal mammals that survived the asteroid. They inherited a broken, empty world. The Paleocene-Eocene thermal maximum, that great, sudden, carbon-fueled heat wave, was the starting gun for their true diversification. It created a world of boundless, interconnected tropical forests, a global buffet, a hothouse nursery that provided the safety, the energy, and the opportunity for an evolutionary explosion. Our own lineage, the primates, began its true journey in those vast Eocene canopies. The global pole-to-pole forest was our first great highway, our first kingdom. It was in those warm, complex, fruit-laden branches that our ancestors refined the traits that would one day lead to us. The grasping hands, the forward-facing, color-discerning eyes, the complex social groups, the brains learning to navigate a three-dimensional world of opportunity. We are, at our very core, creatures of the hothouse trees. The horse, that modern symbol of the open, grassy plains, began its journey as Eohippus, a tiny, four-toed, browsing creature, hiding in the lush, ferny undergrowth of those same Eocene jungles. The rainforest planet was its cradle, its safe haven, nurturing its lineage for millions of years before the first grasslands ever appeared. The whales, the greatest of all ocean mammals, were also born of this time. It was the warm, stable, bountiful, and predator-emptied Eocene seas that invited their terrestrial, wolf-like ancestors to return to the water, providing the perfect, gentle, evolutionary pathway to produce giants like Basilosaurus. The bats that fill our modern night skies, the rodents that rustle in our walls, the carnivores that rule our wildlands, the hoofed animals that graze our plains. The fundamental blueprints for almost every major order of modern mammal were drawn up, tested, and established during this singular, explosive, creative period. It was the fertile, safe, and boundless garden that allowed life, after the great reptilian silence, to experiment with 1,000 new, warm-blooded forms. We are the heirs of a hothouse world. We are the descendants of the creatures that thrived in the Arctic jungles and the Antarctic forests. The subsequent cooling, the rise of the ice ages, the spread of the grasslands. These were merely the second act, the great sorting of the lineages that the hothouse had already created. Our modern icehouse world is populated almost entirely by the hardened, adapted, and specialized children of that one long, spectacular global green summer. The rainforest planet is not then just a lost, strange, and distant memory. It is our origin. It is our shared ancestral home. And it is perhaps also something else. It is a quiet, profound, and deeply ancient reminder, written in the very rocks of our planet, of just how sensitive, how dynamic, and how violently the Earth's climate can change, and how that change, in turn, forever rewrites the story of life. And that story, the story of how this rainforest planet was born, the tale of the Paleocene-Eocene thermal maximum, carries its own quiet and deeply resonant echo. This hothouse world, this global polar jungle, was not an accident. It was the direct, physical consequence of a specific event. It was the result of a massive, geologically instantaneous injection of carbon, of greenhouse gases, into the planet's atmosphere. In the Eocene, this carbon came from a natural geological catastrophe. A methane burp, perhaps, triggered by vast volcanic eruptions in the North Atlantic, cooking ancient buried deposits of carbon and releasing them into the sky. It was a natural planetary spasm. But the planet, in its response, was indifferent to the source of the carbon. It cared only for the physics. The sudden, thick greenhouse blanket trapped the planet's heat. The oceans, absorbing the excess, became acidic. The global temperature soared. The ice melted. The forests migrated. The world, in a geological flash, was rewritten, completely, and irreversibly. This ancient event, buried in the rock record 56 million years ago, is not a parable. It is a data point. It is the Earth's own clear and unambiguous testament, written in stone and sediment, to its own profound and sometimes terrifying sensitivity. It is a quiet geological demonstration that the climate system, which can remain stable for millions of years, is also capable of profound, rapid, and catastrophic shifts when pushed past a critical threshold. It shows us that the world's thermostat can break, that the planet's fever can spike, and that when it does, the consequences for the biosphere, for the distribution of life, for the very coastlines of the continents are not small but total. The Earth, in its own slow time, does heal. The planet did not stay a hothouse forever. The Azolla event, that quiet green biological pump, perhaps began the process. The slow tectonic drift, the great divorce that isolated Antarctica, finished the job, resetting the planet's climate into the icehouse mode we know today. But this healing, this geological rebalancing, is a process that takes millions and tens of millions of years. It is a process of immense, slow, planetary patience, a timescale utterly alien to the fleeting, rapid pace of the life that inhabits its surface. The rainforest planet, then, is more than just a beautiful, lost green ghost. It is a profound, quiet, and ancient lesson, whispering to us from the deep past, a reminder of the delicate, fragile chemical balance that makes our own familiar ice-capped world possible. It is a meditation on the deep, slow, and powerful cycles of the planet itself, cycles of warmth and cold, of fever and ice, that have defined our world long before we arrived, and will continue long after we are gone. That long, slow planetary cycle, that breath of fever and ice, is the ultimate rhythm of our world. And our journey tonight has taken us into its warmest, greenest, and perhaps strangest phase. We have walked through the impossible, dreamlike reality of the rainforest planet, a world that truly existed, a world of almost unimaginable global warmth. We have stood in the great silence of the Paleocene, the empty, hopeful world that followed the dinosaurs' demise. We felt the sudden geological fever of the PETM, the great methane burp that lit the fuse, and watched as the planet, in response, bloomed. We have journeyed to the ends of the Earth and found not ice, but a paradise. We have stood in the lush, green, nothofagus forests of Antarctica, a world of cool, damp, and total winter darkness. We have drifted through the even stranger, subtropical cypress swamps of the high Arctic, a place where alligators and turtles slept, waiting, in the warm, humid, 3-month-long night for the sun's eventual return. We have felt the sheer, monstrous, reptilian power of the equatorial hothouse, the world of the car-sized turtle and the bus-sized snake. And we have seen, in the quiet, dappled light of the German jungles, the tiny, humble, four-toed dawn of the horse, and the first, grasping, agile steps of our own primate ancestors. And finally, we watched as this entire, magnificent, 50-million-year-old green dream, this hothouse world, was slowly, patiently, and irreversibly dismantled, not by a catastrophe, but by the simple, inexorable continental drift that isolated Antarctica, birthing the cold and plunging our world into the icehouse age we still inhabit today. The rainforest planet is gone. Its warmth has faded. Its polar jungles are buried beneath 3 kilometers of solid ice, their fossils a silent green testament to a world that defies our modern logic. Let the memory of that world be a comfort now. Let the idea of a planet so warm, so green, so full of life be a gentle, encompassing thought. The silence of that ancient Arctic forest in its long, warm polar night, Let that profound, deep, and peaceful stillness merge with the quiet of your own room. The Earth has known profound fever. It has known profound ice. It is a planet of cycles, of deep, slow, and endless change. But tonight, for you, there is only this moment, this stillness. The journey is over. The hothouse world has faded, its green ghost returning to the deep past. There is only the quiet of the present, the comfort of your rest, and the gentle, welcome, and peaceful embrace of sleep. Rest now. Good night.